Hello everyone. So last time we looked at limit laws, and they were useful tools for helping us to find complicated limits from simple ones, but they still had a couple of reservations where we couldn't apply them. For instance, the limit of a quotient was the quotient of the limits, but only if the limit of the bottom was non-zero. And we had this direct substitution property where for nice functions we could just substitute in to find the limit, but that only worked for polynomials or for rational functions where the bottom was non-zero at the substitution point. And often those are easy limits when we can use these rules, but there are lots and lots of harder limits where they don't apply, and often those are the most useful that we have to find, for instance, when we're doing calculus. So in this section, I want to go through a couple of strategies for finding these more complicated limits. And there are going to be more strategies throughout the course, but for now, we're just going to look at using algebra to find some of these limits. So let's see some of these techniques. So the first example, the moral is going to be canceling factors. So for example, let's look at the limit as x tends to 2 of x squared minus 4 divided by x minus 2. And if we want to go back to the tools from the last video, well, we can't use the quotient rule. I mean, we cannot say it's the limit of the top divided by the limit of the bottom, because the limit of the bottom would be the limit of x minus 2 as x tends to 2. That will be 2 minus 2, that will be 0. So we can't apply that rule. And also, we can't apply direct substitution because it is a rational function. But 2 is not in the domain of this rational function because the 2 would be, x minus 2 would be 0. Okay, so we cannot use any of the tools we've had so far, so we have to do something else. But okay, if we look at this example long enough, we see that the top, the x squared minus 4, well, we can factor that as x minus 2 times x plus 2. So let's do that. So we write it as x plus 2 times x minus 2. And then on the bottom, we also had x minus 2, right? So we have an x minus 2 on the top, and we have an x minus 2 on the bottom. So we can go ahead and cancel those, and we're just left with x plus 2. And here I wrote this is equal to what we started with, provided x is not equal to 2. So here I'm being really careful because the expression we had on the left, it wasn't defined when x equals 2, right? 2 was not in the domain of the function we had on the left because if we try to substitute 2 in, we get 0 over 0, it wouldn't be defined. Whereas the function on the right, the x plus 2, that is defined at x equals 2, right? If we substitute 2 plus 2, we get 4, it's perfectly defined. So then they don't agree at x equals 2, but they are the same everywhere at x not equal to 2. Unfortunately, that's good enough for us because remember, when we're trying to find the limit as x tends to 2, we care what happens when we're very, very close to 2, but we don't care at all about what happens at x equals 2. Okay, so that's a general fact about limits, remember. We care what happens close to the limit point, but we don't care what happens when we're at equal to the limit point. Okay, so instead of calculating the limit of this complicated expression, we can instead look at the limit instead of x plus 2, because they're equal when we're close to 2. So instead of looking at one, we can just look at the other. Okay, now we can find the limit of x plus 2, and let's just forget completely where that came from. We have a separate problem, find the limit of x plus 2 as x tends to 2. Okay, x plus 2 is now a polynomial, and we know with polynomials, we can just use direct substitution. So we can substitute that 2 in, we get 2 plus 2, we get 4. Okay. So here the moral was, if we can, cancel factors, factorize and cancel some factors, that's often helpful for finding limits. So here implicitly we use the fact that if two functions agree except at the limit point, then the limits are the same, right? We had two functions, x squared minus 4 divided by x plus 2 divided by x minus 2, and we had x plus 2, and they agreed everywhere except for the limit point 2. Okay, the limit points were the same because we never care what happens at equal to the limit point. With limits, we only care about what happens close to the limit point. Okay, so let's see a few more examples. So the next one is based on expand and cancel. So if we look at 4 plus h squared minus 16 divided by h, it's the same story if we try to use the tools from the last section. So we can't do the limit of the top divided by the limit of the bottom because both of them will be 0, right? And the quotient, we cannot use the quotient rule for limits, whatever you want to call it, if the limit of the bottom is 0, right? We have to have the limit of the bottom is non-zero. So we can't use that rule. And also, if you were to expand, you'd see it's a rational function, but h equals 0 is not in the domain of this rational function. So we can't use any of those tools. We have to do something else. So let's expand and cancel, right? We have a square. So let's try to expand the square. So we have 4 plus h squared minus 16 becomes 16 plus 8h plus h squared. Remember, we get 2 copies of the 4 times h, so we get 8h. And then we still have the minus 16. Okay, now we have a 16 and we have a minus 16. They're going to cancel. We're just left with 8h plus h squared divided by h. Okay, now everything is divisible by h on the top, so let's divide by h. Let's cancel the h. That just becomes 8 plus h. And here, to be really careful, I should say these are all equal if h is not 0, right? The thing we started with was not defined at h equals 0. This now is defined at h equals 0, but they're the same everywhere else apart from h equals 0. Okay, and now since we don't care about that at the limit point, instead of trying to calculate the complicated limit, we can instead calculate the limit of 8 plus h instead. Okay, forget about where this came from. The limit of as h goes to 0 of 8 plus h. 8 plus h is a polynomial. We can do direct substitution for polynomials. We substitute in h equals 0, we get exactly 8. Okay, so now we managed to find the limit of this expression. So if we have parentheses and squares, maybe cubes, but you don't really want to go any higher than cubes, sometimes expanding and canceling is the way to go, especially for squares. Okay, so let's look at another example involving roots. So here we have the square root of x squared plus 9 minus 5 divided by x plus 4. And we're looking at the limit as x tends to minus 4. And well, it's not a rational function, so we can't try to do that. But if we were to try to use, the limit of a quotient is the quotient of the limits, again, the limit of the bottom here would be 0. So that's not allowed. We can't do that. So again, we have to do something else. Here, the trick is to rationalize the numerator. So let's multiply top and bottom by the conjugate of the numerator. So multiply by the square root of x squared plus 9 plus 5. Okay, and as long as we multiply the top and bottom by the same thing, we keep it equal. So let's go ahead and do that. Sorry for the mess. So we multiply top and bottom by the conjugate of the numerator. And then let's multiply out and see what we get. So we have a square root of something times the square root of something. So we just end up with the something, which is x squared plus 9. Then we have a square root times 5 and a square root times minus 5. So those cancel. And then we have minus 5 times 5. That's going to become minus 25. So that becomes the top. And then on the bottom, okay, there's nothing nice to do. There's just x plus 4 times this huge mess, which we just copied. Okay, and then if we go back and look at the top, we have x squared plus 9 minus 25. That becomes x squared minus 16. So that's x plus 4 times x minus 4. We can factorize it as. Okay, now we're in a good position because we see on the top an x plus 4. We see on the bottom an x plus 4. We can cancel those, and that agrees with whatever we started with, as long as x is not equal to minus 4. Okay, and we're trying to find the limit as x tends to minus 4. So we don't care what happens when x equals minus 4. So we're all good. So we're left with x minus 4 divided by the square root of x squared plus 9 plus 5. And now we are more fortunate because if we try to substitute x equal minus 4, now the bottom is non-zero. Okay, so now we can use the limit laws. Instead of taking the limit of this complicated mess, we can do the limit of the top divided by the limit of the bottom, because now the limit of the bottom is not 0. Okay, so if we do the limit of the top, the limit of x minus 4 itself is a polynomial, so we can just substitute. So we get minus 4 minus 4, we get minus 8. And then for the bottom, we're going to calculate the limit of a sum. And so we're going to look at the limit of the square root plus the limit of the 5 separately. The 5 is a constant, so it just stays 5. Then we have to look at the limit of the square root of x squared plus 9. Okay, we can bring the limit inside the square root. So we have the square root of the limit of x squared plus 9. X squared plus 9, it's a polynomial. We just use direct substitution. X squared plus 9 tends to 16 plus 9, which is 25. So we're going to get minus 8 on the top. We're going to get the square root of 25, which is 5, plus another 5 on the bottom, minus 8 divided by 10, or minus 4 over 5. So here the strategy was, if there are these square roots, often it could be good to rationalize them. So multiply the top and the bottom by the conjugate of the root. So that means change the minus to a plus. Okay, here's another topic, maybe slightly moving away from using algebra, but still kind of a related trick, is if we have a function which is defined in pieces, say it's there's one formula on the left of a number and there's another formula on the right of a number. It's hard to think of both pieces at a time, but if we split the two-sided limit into two one-sided limits and analyze them separately, then we can just think of one of the pieces at a time. Okay, so let's try to do that with the limit as x tends to 1 of this function. And you see that it changes at 1. Okay, so let's split it. Let's consider the one-sided limit on the left and on the right separately. So if we look on the left, then we're looking at the limit as x tends to 1 from the left of f of x. That means we're interested in what is the function getting close to as x gets close to 1 with x less than 1. Okay, and here we're only caring what happens when x is less than 1. We don't care about what happens when x equals 1. We don't care about x bigger than 1, only with x less than 1. Well, if x is less than 1 and it's close to 1, this function is just x squared. So we're just looking at the limit as x tends to 1 minus of x squared. Okay, and then it's a polynomial. We can use the limit laws, the direct substitution property. We substitute in, we get 1 squared, which is 1. So this is our one-sided limit. And then on the other one-sided limit from the right, okay, if x is tending to 1 from the right, we're looking at x close to 1 but larger than 1. If x is larger than 1, then instead we're using the formula x minus 2 squared. So we're looking at the limit instead of x minus 2 squared. Okay, x minus 2 squared, if you want to multiply out, again, it's just it's a polynomial. You can use direct substitution. So we substitute in x tends to 1. From the right, we get 1 minus 2 squared minus 1 squared, we get 1. And now we have both of the one-sided limits are equal. And remember, if the two one-sided limits exist and they're equal, then the two-sided limit exists and is equal to the common value. So here we can say that our two-sided limit exists and it's equal to 1. So the moral was, if we have functions which are defined in cases like this, you can analyze either side separately by thinking about the one-sided limits, and then based on the one-sided limits, make your conclusion. So here the one-sided limits were equal, so the two-sided limit exists. If these had been different numbers, say in a different example, say we got 1 and we got 2, and they were not equal, then we would have said the two-sided limit does not exist. Okay, so here was what we used, right? The two-sided limit exists if and only if both one-sided limit exists and are equal. Okay, so that's it for this time. So remember, if the limit laws or direct substitution property don't immediately apply to that, to one example you're looking at, you can try to use some algebraic techniques, or maybe if the function is defined via pieces, split into one-sided limits. Thank you, see you next time.